So the basis of my research was actually this functional, which you can see here, which is called Helfrich functional, and this Helfrich functional describes the optimal shapes of vesicles, and vesicles are objects, are model approaches for biomembranes. And the question was, how can we adapt this functional to two-phase flows? And if we can do this, is there any chance to describe wet blood cells in blood flow, which you can see here? So here are the red blood cells, and we can regard them as a two-phase flow, where one phase is the cytoplasm of this red blood cell, and the other phase is the blood plasma. And another application could, for example, be the description of motile cells, which you can see here as a crawling cell, and you can also regard them as a two-phase flow. And finally, are there any chances to describe active swimmers, particles which are active driven by some, which you see here, some arms like this. Okay, and here is the outline of my talk. So first I want to give you a short introduction in these diffuse interface models for the Helfrich energy, and then I want to expand these models to two-phase flow models, and then I want to show you these applications which we see here, so cell motility and flow of multiple cells, which then we can show the flow of red blood cells and, for example, swimmers. Okay, so first here again the Helfrich energy, and what we see here is is this vesicle, which is our model approach for a biomembrane, and this vesicle consists of a lipid bilayer, which you can see here, where we have here these small lipids with their hydrophilic head, it's green, and their hydrophobic tail, and they are based in aqueous solution. And then we can write down this energy, which was derived by Helfrich and also by Canham and Evans, and where the first, where here this term H denotes the mean curvature, Bn is the bending rigidity, and of course H naught denotes the spontaneous curvature, and with the spontaneous curvature we are able to describe asymmetry. Yeah. For example, certain proteins acting on this cell membrane. And last but not least, we have here this term with the Gaussian bending rigidity, but we consider no topological changes for our model. Therefore, this term is constant for every surface, and then we can neglect it. We have to deal with other constraints. For example, we have volume conservation due to the impermeability of the membrane, where you said the cell interior is constant. And of course, we have a global surface conservation, where we said that the surface area is also constant. And then the goal is that these vesicles, supposed as the surface, minimize this energy. Okay, and we want to calculate those models, those optimal surfaces, by using this phase field approach. And here I want to give you a short introduction of this phase field approach. So consider the cell interior or the cytoplasm. It's denoted by the domain omega-1, and then the extracellular matrix is denoted by omega-2. And we introduce a phase field variable phi, which labels each domain with 1 inside and -1 outside, and between these domains we have a diffuse interface. So this is why phase field models are often called diffuse interface models, and this interface is here. You can see it's continuous and it's smeared out, and then we are able to implicitly define our surface gamma by the zero level set of phi. Yeah? And then we have an interface parameter epsilon, which characterizes the thickness of this interface. And the phase field method provides nice features, which we can see here. So we can easily calculate the normal vector, the curvature, and as well the surface delta function. And here you see some examples where we can approximate this one-dimensional surface by this phase field variable, and of course this two-dimensional surface by this phase field variable. And the goal is that we should show that if epsilon goes to 0, our diffuse interface problem then converges to the sharp interface problem. Okay, here are some facts about these phase field methods. So yeah, the phase field method is a method where we can treat free boundary problems, and it has some advantages and disadvantages. So for example, yeah, we construct our models from an energy minimization approach. It is of course easy to implement it with our standard FEM tools, and we can easily deal with topological changes, and we can also extend the models from 2D to 3D without any problems, like every level set method. And of course, it is simple to couple it to additional equations. And there are of course some challenges or disadvantages because of this interface. We have to deal with gradients, with high gradients. Therefore, we have to refine our grid in this region, and as this is computationally very expensive, and we also have to deal with small time steps. And of course, the phase field method is an additional approximation to our model, but the error in this approximation is usually much more smaller than the error we do with our model assumptions. And then we can write down this diffuse energy for our Helfrich functional, which is done here. So again, you see here the bending rigidity, and what you can prove, yeah, for simplicity, we neglected the spontaneous curvature, and what we can show is that this diffuse interface energy then converges for epsilon to 0 to the sharp interface energy. And in order to calculate minimal surface, we have to calculate the variation of this energy, and this is done here. And so we can calculate this, and then we arrive at the diffuse interface Wilmer flow. And again here, along the interface, that is where phi is equal to 0. If epsilon goes to 0, we arrive here at the sharp interface Wilmer flow. And then we construct our evolution equations by calculating the time derivative of the energy. This is done here, and we claim that this energy is less equal 0. And here the flux dt phi is unspecified, and we choose it like here. And if we plug this term in, we see that the energy is less equal 0, and that is how we construct our evolution equation. Okay, and then if the variation is equal to 0, we arrive at our minimal surface. In that case, we can prove that the shape of our phase field function is this hyperbolic tangent, where r of x is a signed distance function. And then we can do this for some surfaces, and we get nice results. So we see here, so you can here prove or show some problems which are usually occur in differential geometry. So you see here two balls, and these two balls of course merge, and we arrive at a sphere here, and we can show also analytically that this Wilmer energy is bounded by 4 pi for surfaces with genus 0. And of course, if there is a hole in it, so the surfaces have genus 1, then the minimal surface of this Wilmer energy is a torus. And you can also analytically calculate this energy. Okay, but now we have to deal with our constraints. So we first have to translate it in our diffuse approximation. So the volume of the cell interior can then be approximated by integrating over phi, and then we set it constant. Yeah, and in our model approach, we can then apply an h-1 gradient flow, which means that we just replace the minus gamma by gamma Laplacian of the variation, And then you can show that the time derivative of phi over the domain is equal to 0.
Could you comment? You're saying the volume of, is it the are you talking of the volume constraint of the cave, or the volume inside
the volume inside the surface?
But your phi is -1 somewhere outside. Are you taking into account the outside region, because phi is?
Yeah. This is this. Of course, we integrate over the whole domain, but you can show this is. We do not have to integrate over the cell interior. It's actually the same. So if we integrate over the whole domain and phi is constant, that means that our volume is conserved.
So this could be negative, in fact.
Sorry?
So this value could be negative, because if you have a very large portion of negative values of phi, whereas -1, for instance, initially, then it could be negative.
Yeah, then it could be negative,
yeah,
sure.
Okay, but indeed that integral is preserved, conserved.
If the integral is conserved and the phase field is between -1 and 1, then this means that the interior is also conserved.
Thank you.
Okay, and then the surface area constraint, we approximate this surface area by the Canhilliard energy, and then we can construct a penalty term, which is done here. And if the A naught is our deserved surface, and if this term is equal to 0, then the energy is minimal, and then we conserved our surface. And you can also construct a penalty term for the volume of the cell interior, but then you have to deal with 2 penalty terms, and this can somehow be challenging. So that is why we apply those H-1 gradient flow. Okay, and then we can write down again this diffuse Helfrich energy with our surface constraints, and then the evolution equation looks like this. Yeah. Okay, and then we can again solve our minimization problem, and if we consider again these 2 surfaces here, they again will merge, but what they now build is here kind of a cigar-shaped surface. And of course, in 2D and 3D, if we start with an ellipsoid, then we arrive at these discocyte-shaped surface, which reminds us to a blood cell.
So you don't fix topology in any way?
I don't fix what?
You don't fix the topology of the surface. So if you start with a surface of genus 2, what stops it becoming a surface with no hole? Because you have a lower...
Usually I start with a surface with no hole in it.
Sure.
And of course, if the surface constraint is a bit rough, then it can happen that a hole occurs. So the energy will minimize, and then it could be that the energy of a torus is less than the energy of the surface with the constraints in it. Okay. And then you have to again have a look at this H naught, the spontaneous curvature, and if you set it in a certain way, then you will prohibit this building of holes. Okay, so I mean this is quite nice, but what we wanted to do is we want to embed these functional in 2-phase flows. Yeah, so in order to simulate those red blood cells. So we now consider the cytoplasm of the cell and the extracellular matrix as fluids with certain densities and viscosities, and then the cell membrane is regarded as a fluid-fluid interface. So consider here the Navier-Stokes equation for each domain, and then we have to deal with jump conditions along the membrane. So the first condition is that the velocity jump is equal to 0, and the second condition is that the stress tensor times the normal vector is then equal to the mean curvature flow of this Canhilliard energy if we want to describe normal fluid flow, simple fluids. Yeah? Then we have here the surface tension of this interface, and in our case we want to describe fluid membranes, then we just use the variation of this Helfrich energy with the constraints, and then we can write down these jump condition. Yeah, where this is the sharp interface Willmore flow, and this is the flow which results from the volume constraint. Yeah, and but these were the sharp models, and we want to describe diffuse models and how can we construct them. This is done here. So consider now the free energy of the system, which here consists of the kinetic energy of the fluid, just denoted here. Of course, for simplicity, we set the density to be constant, and here again the Helfrich energy. And when we, if we derive it with respect to time, then we claim that this term is less equal 0. Yeah, and what we now do is we insert our equations we already know. So this is the momentum equation, and this is the equation for the phase field phi. And here are some variables, for example, the body force F and the flux J, which are yet unspecified. And we want to calculate those parameters in order to get a model where the energy is decreasing. Yeah? And if we plug in these equations to this term here, then we arrive at the first line here. We remove all terms which are 0, and then we have this equation here. So the first guy is already less equal 0, which is nice. And then we have here this body force term F. And if we set F to this term here, and this term also vanishes. And of course, if we set J in this way, this guy is also minus less equal 0. And then we can write down here our thermodynamic consistent model, where we plugged in here these terms, which, yeah, these unknowns we now know. Okay, and then there has an energy law, which looks like this. So the energy is minimized just by the viscosity and the variation of the energy of the bending energy in the Willmore equation. Yeah, and what please note that we usually use a mobility coefficient gamma, which is really small. That means that the physics of the membrane, which is here represented by the body force, that the physics is only done by the Navier-Stokes equation, and that this Willmore, this phase field equation here is just advects the interface. Yeah, and then we can also write down the viscosity, which is now an interpolation of the bulk viscosities with the phase field function. Okay, so that was our model H, and now we want to extend this model H in order to describe crawling cells. Yeah, and here's a nice sketch how this cell motility, about the basic processes during cell motility. And yeah, I found this sketch here in a paper, in a nice review paper, and yeah, what we just here, the basic processes are, of course, actin polymerization in the cell front. So you see here the actin meshwork, the polymerize in the front, protrude the membrane, and on the other hand, we have creation of new adhesion sites at the cell front, and the relief at old adhesion sites at the cell rear. And finally, there's also contractile stress between these actin filaments caused by a myosin, which pushes the body forward. Yeah, and what we want to do is, in the first model, we want to focus on the first two facts, so the membrane protrusion and adhesion. And in the second model, I want to show you we describe this contractile stress within liquid crystal approach. Okay, so but first, please note that the Helfrich energy for this approach is not that we have to extend it in a certain way. So we don't have any surface area conservation of the cell membrane, because the membrane is highly in motion, and there are the membrane here is not really flat at certain points, which is called invagination. And of course, there are new lipids coming from the bulk which attach to the membrane. Therefore, we consider an extensile membrane and use a surface tension term, this one. And this can, of course, be approximated by here by our Caneliot energy. Okay, and then the evolution equation looks like this. Okay, and for the actin polymerization, can you see it? No, you can't. But here are these actin filaments, and of course here's the cell membrane, and they polymerize at the front and push against the membrane and protrude it. And what we suppose is that these active GTPases, maybe you can see it here, these active GTPase proteins regulate this actin polymerization. Yeah, and we say that the concentration of these active GTPase is related to the strength of the membrane protrusion. Yeah? And this can be modeled in, which we see here. We just add this term to our Navier-Stokes equation, and that means that where the gradient of phi is not equal to 0, that is where the interface is, we have a force which acts normal to the interface, and this force, of course, is related to the active GTPase, which we denote with C1 and the parameter alpha. And adhesion is just simplified by a normal friction force. Yeah, and then we are able to describe cell motility if this concentration of these active GTPases is not equal along the membrane. So we use a kind of a polarity, and then we use a network model which causes a Turing type instability, where we have these certain concentrations of these active GTPases. Yeah. And this is the network model we have. So consider here this cartoon here. So this is the cytoplasm or the cell bulk, and within this bulk we have capital C, which is the inactive GTPase, the cytoplasmic GTPase, and this is described by the first equation. So this can diffuse and attract along the bulk. And of course we have the C2, the inactive membrane-bound GTPase, and C1, the active membrane-bound GTPase. And of course they can also attract and diffuse along the membrane. And here is a reaction term denoted by H, which describes the activation-inactivation process. And then we see here that these inactive GTPase can attach to the membrane and can detach from the membrane. And this is described by this term Q here, which is a Langmuir adsorption-desorption law. And this is then a reaction term within this equation of C2. And you see here, it's a boundary term of the bulk equation. And what is nice is that this model leads to Turing type instabilities for equal diffusion coefficients for equilateral diffusion. And of course, we assume the bulk diffusion to be faster than the surface diffusion. And this model we found in a paper by Ritz and Röger. Okay, and yeah, and the model we see here again, this bulk equation holds in omega-1, and omega-1 is also time dependent, and the other equations hold on gamma, on the surface gamma, which is also time dependent. And then we apply our phase field framework to this equation, and then we can nicely extend these equations to the whole domain omega. And this is done here. So consider psi is a transformation of this phase field. Again, the range of the phase field variable is from -1 to 1, and we translate it to 0 and 1, and then this function is a representation of the characteristic function. Yeah, and if we plug this characteristic function in the equation for capital C, then we are able to extend it to the whole domain omega. The boundary term is now included in the equation by this term, where capital psi is the delta function. And of course, we can extend the equations which hold on the domain gamma we can extend it to omega by using the surface delta function. Yeah, and what is really nice that the mass here is conserved of c, and this system, if we have the right parameters, produces our instability, our Turing type instability. And again, here's some implementational aspects. Of course, so we implemented these equations. Again, we have another Stokes equation, we have an equation for the phase field, and we have an equation for the concentration. And we implemented in our FEM toolbox AMDIS, we use a semi-implicit time discretization. That means all terms are treated with an implicit Euler, and all nonlinear terms are linearized. And of course, these equations are highly coupled. But what we do is we use an operator splitting approach. That means that we first solve the Navier-Stokes equation, update the velocity field, plug it in our phase field equation, and solve the phase field equation. And this is then inserted for the calculation of the concentrations. Yeah. And of course, we use adaptive mesh refinement along the interface and use linear solver UMFPAC. And what we get here is first results. So what you see here is our initial condition, the circular shaped cell. And here is the active GTPAs, and this is the inactive GTPAs along the membrane. And here you see the bulk GTPAs and the velocity field.
So why is it preferentially moving in there?
Yeah, that is why we added some noise to the right-hand side of the cell. Usually the Turing instability, it's created on a certain point in the membrane, but we wanted that this is just on the right-hand side. And then this instability increases, the concentration increases, and again here this instability is nearly stable, and this leads to a force in the normal direction at these points, and this protrudes the membrane because it induces a flow in the Navier-Stokes equation, and that pushes the cell. And we can show you as a movie. And here the cell reaches its stationary shape. Again, this is the active concentration, and this is the fluid flow. Okay. And what is also really nice, I found it in a really nice paper here. And we can also add, we know that these cells are really following chemoattractants. So if we have a concentration of a chemoattractant, which is denoted by C tilde, we can nicely add this term to the attraction of the active GTPAs. And then we can describe cells which are following those chemoattractants, which you can see here. So for example, if we use a chemoattractant which direction is changed randomly, then we can generate those motions here. Okay. And of course, this is what we found in an experiment. So this is a microtube, and within this microtube there's a gradient of these chemoattractants, and we see here that this cell tries to follow this gradient and moves into the micro tube. Yeah, and we wanted to show this with our model. So this is actually the concentration, and we see here, okay, the cell immediately begins to follow this chemoattractant. But of course, what you see here, the cell body looks completely different to the cell we've already seen. So maybe this approach as a viscous fluid is, in this case, not so convincing. And of course, we can change parameters within our GTPAs network. For example, if we increase the concentration of the diffusion coefficient of C2, then we can create different patterns, and with these different patterns we are able to maybe describe not a crawling cell, but a cell which tries to build these philopodia-like structures. Okay, so this was the first model, and I now want to show you the second model we were working on. And this model focuses now on the contractile stress within the cell. So we know we have contractile stress between these actin filaments, which is caused by myosin, and there have been experiments where they found out that these solutions of actin and myosin can create instabilities, spontaneous instabilities, and if these instabilities are stable, then they induce a fluid flow, and this fluid flow is supposed to be responsible for cell motility, especially in 3D without any adhesion to the substrate. And how can we describe such solutions of actin and myosin? And this is done here. We use the liquid crystal theory. And maybe you can see it here. So this is a solution of such liquid crystals, and these actin filaments are regarded as those liquid crystals. These are small rod-like particles, and they are denoted by a director field capital P. And the special about this liquid crystal is that, in contrast to normal fluids, translation of this liquid crystal can cost energy. And this is called a distortion stress. And there is an energy which is called Frank energy, which describes these liquid crystals. And this you can see here. And we combine this energy of this polarization field with our phase field by adding this phi to the double well potential of P. And then this leads, then we have, if we do this, we have P, which is here. You have here the cell bulk, and the magnitude of P within the bulk is 1, and outside the bulk, where we don't have any solution of actin filaments, the magnitude is 0. And this you can see here, for example, if we have here the bulk of the cell, these small arrows are the director field P. Yeah, and the elasticity of these filaments is described by this term here, where K is an elasticity parameter. And of course, we have another term with a parameter beta, and this term is responsible for to the fact that these filaments are aligned in normal direction along the interface. Yeah, and this was the model for the director field P, for the polarization field P, and we now add an active stress to our model. This is then included to the Navier-Stokes equation, and this active stress causes the instability. And therefore, here's some, so this described by these terms, and here are some cartoons. So consider first 2 actin filaments, and they are connected with a myosin motor here. And this myosin motor causes a contractile stress, and as a result of this, we have here such a fluid flow of of a quadrupole. Yeah, and this quadrupole is balancing all forces, and nothing happens. Yeah, but if a bundle of those actin filaments is here inclined, then this force balance is broken. This quadrupole looks a bit different, and we then have a stable fluid flow in one direction. Yeah, and if this is stable, it's supposed to be that this effect is responsible for cell motility. Yeah, and then we construct again the model like our model H. So we consider a free energy, which now consists of this energy, this Frank energy, and we do our same approach and use the equations we already know, and we extend these equations by the equation of this polarization field P. And what you see here is just a simple advection term of P, and of course denoted by K, which is the antisymmetric stress tensor, which accounts for rotation. If the velocity field is rotated, then we have to see this within our P, and this is also called co-rotational derivative. This term describes flow alignment. For simplicity, we set it to 0, and again, a flux we just want to determine in our approach. Okay, and if we do this, we arrive at the following equations, which look a bit complicated, but I colored the new terms to our previous model H, and again, we have our Navier-Stokes equation, we have the body force coming from the membrane, and then we have here, which is called distortion stress. This looks a bit similar to the body force term here, and this is the active, contractile stress term, where Fa and Re are now non-dimensional parameters. Re is the Reynolds number, and Fa is a non-dimensional activity number. Yeah, and these are additional stresses, which you don't mind, and of course, this is the equation for the orientation field. And the elasticity here, again, parameter Pa, but the variation of the elasticity is now denoted by a Laplacian. Yeah, it's clear if you have two filaments and they are in that shape, it's clear that a diffusion of these filaments will cause a motion the spheres then that they are equal aligned, and this minimizes the energy of these Frank energy. Okay, and then we again consider a circular shaped shell.
Just to understand this, the filaments are freely in the fluid.
Yeah, we suppose that these filaments are it is a solution of this filament, and this solution covers the whole cell body. So the cytoplasm consists of a solution of these actin filaments.
Dissolved, or what do you mean by solution?
Yeah, I mean that these filaments are within a fluid, and this fluid covers the whole cell body. Yeah, okay, and then we start with our circular shaped shell. The filaments are here equal aligned, yeah, and then we start the simulation. Okay, what we see is, maybe I just show you the whole movie and then I want to explain it. Yeah.
Do you physically represent the filaments, or?
Yeah, these filaments are physically represented by these liquid crystals, and the representation is done by the stresses we add to the Navier-Stokes equation. Yeah, and again, the contractile stress at the beginning causes the quadrupole here, and this quadrupole leads to the fact that the cell becomes stretched, and after a while, because of the feedback of the membrane tension or the bending part of the membrane, we reach here a stationary shape, and here there also occur 4 vortices within the cell, and they are responsible, we will see it later, I'm going to explain it again. Then we have here a instability which is called splay instability, and this instability causes a fluid flow. And of course, what we see here is that it's not really clear which direction we get by starting this simulation. So we can also have a reverse splay, which we see here, and then the cell moves to the left. Okay, and how can we understand this? So again, here is a sketch. Consider here our circular cell. Again, here are the quadrupole. This quadrupole stretches the cell, and because of the membrane feedback, four vortices occur. And these vortices are responsible that these bundles of the filaments are inclined or declined, depending on which side you look. And yeah, depending on which side actually dominates, we get a inverse splay or a splay like here, where the cell now moves to the right or moves to the left. Yeah, but this instability only occurs if the parameter, for example, if the active parameter reaches a certain value. Yeah, so if this if the activity is strong enough, then the vortices are strong enough to incline these filaments and then produce this instability. Because we have diffusion of P on the other side, or which is related to the elasticity of the filaments, this diffusion works against this instability, because it will equally align these parameters. Yeah, and then we have here the diffusion of P, and on the other hand, we have the advection and rotation of P, which is caused by flow, and these two counterparts are then responsible if the stability occurs or not.
So you can have, for instance, the top segment of the cell is moving faster, the fluid is moving faster there than the bottom cell. You get a swing, right?
You could, but what we observe is that this instability here is really stable. Yeah. That this direction is stable, and this only means that the cell moves in one direction.
In one direction.
Yeah. But of course, if you have another flow, a fluid flow, then these can be translated, rotated, and then the cell moves in another direction. Yeah, you could use it, for example, in order if you have two cells and they collide, and you have one polarization field, and between this collision, then there's diffusion, and this diffusion causes a rotation of the splay parameter of the splay, and it means that you can model a kind of elastic collision. Yeah. And then you can do those simulation for different activity parameters. What we see here is kind of a Hopf bifurcation. Yeah, so the instability occurs only if the activity is below a certain value, which you can see here. And there is the other colors are the parameter beta, which is which smooths out this transition. And of course, you only see here the magnitude of the velocity at the stationary point if the cell is moving. But what we get in our model is that the velocity, of course, that the cell moves to the left, which you see here, to the right, which you can see here, to the left. This is depending on the initial conditions, and usually we add a bit noise on it, therefore we get these results. Okay, and we did some other simulation. For example, there's the parameter epsilon, which labels the width of the interface, and we want to find out if this instability is stable with respect to epsilon. Yeah. They should be, of course, but we wanted to prove this, or to do some simulations, and we could show that if epsilon goes to 0, that we get a stable critical activity parameter. And of course, this instability is heavily depending on parameters which influence the flow. Yeah, for example, if we change the velocity inside the cell, then we have the same activity, the flow would decrease, and then we don't obtain any instability. But and this we see here, so we have to increase the activity parameter such that we achieve those instability.
If you decrease your epsilon, then you also have to increase your local grid resolution, right?
If
If
we,
you decrease your epsilon value,
Yeah.
which is the thickness of your interface,
yeah,
you also have to increase the resolution of your mesh.
sure, of
Yeah.
course, yeah.
So that was also.
This was
Yeah,
also
yeah.
done. So
Yeah, yeah.
usually I mean, you see here, this
Yeah.
this is depending on, I
Your
guess, the
mesh
square root of 2, and the square root of 2 is a parameter where, which is depending on our mesh size. Okay, so these were the models where we wanted to describe cell motility, and another nice application of this model H we know is the construction is the construction of models which describe multiple cells. For example, we first focus on passive fluids in order to describe multiple red blood cells in a flow in a vessel. Yeah, so what we do is we introduce multiple phase field variables, denoted by the subscript I, and then we are able to give each phase field its specific physical properties, like density, viscosity, bending rigidity, surface tension, and so on. Yeah? But what we now have to introduce is an interaction energy which prevents the cell from overlapping. Yeah? And this is denoted by subscript int. And then we consider the energy of our system, which now consists of a vector of phase field variables, and then denoted by the sum over I. And we have here again the Helfrich energy, and here the interaction energy. And okay, then maybe skip this, but we can here construct this interaction energy. If we consider the phase field I, we are able to calculate the interaction functions coming from all other cells. Yeah, and they are denoted by Wj. And this Wj here is an exponential. It's called Gaussian potential. Yeah, and this Gaussian potential can be constructed by having here the sign distance function coming from cell K or cell J, and because the hyperbolic tension is bijective in this interface, we can then calculate this distance of this cell to our observed cell. Yeah, and so we can see it here again. We have our cell I, cell K, and cell J, and within this interface, we are able to calculate the distance, how far away are those cells from our boundary, and then we can construct this function W, and with that our interaction energy.
I guess this distance calculation is very expensive, isn't it?
No, it's not so expensive. I mean, this distance, you can only calculate this distance if the cell is close enough to our observed cell. Yeah, and this is only if
So, but how do you know if the cell is close enough to your
Yeah, that is a good
right?
question. Yeah.
Exactly.
Yeah, it's a good question. We just use all cells and calculate the sign distance function, but then we set it to 0 if it is not close to the interface. So yeah, but you can think about it, what you could do in order to prevent this calculation. But this is it's not so expensive because we treat these terms, of course, explicitly. So there's no implicit coupling of this. Yeah, and then our model H comes to, we then here have the sum of all body forces coming from the membrane, where we now have here the interaction potential. This interaction potential causes, if our cells are close enough, causes a fluid flow perpendicular to the cell surface, that if two cells are close enough, they don't merge. And here this interaction energy can be calculated like this. Okay, and then, for example, the viscosity here has to be interpolated between different phases. Okay, here are some numerical facts, because the introduction of different phase field variables seems disadvantages. Yeah, it's clear, but what we use is we use first an operator splitting approach, means we solve each problem separately, and then we can use an OpenMP parallelization. So it means each problem is solved on a different core, and we also use different meshes. So it means that we only refine at the interface for one cell, and create a mesh, and this mesh is only related to the cell, which you can see here. So, for example, if we have this is the variable which contains all cells. It's kind of maximum function over all phase field variables, and then usually the mesh looks like this. And if we want to solve the problem for one phase field, we won't use this mesh. In fact, we then create a mesh like this. And this mesh is only used, it's a union of all meshes, it's only used to solve the velocity field. Because
So do you interpolate between meshes?
No, we don't interpolate, we use an assembling process between these different meshes. So we don't lose any information during this process. So this is, it's called multi-mesh strategy, and we submitted the paper. There's also a paper of Axel Vogt and Thomas Witkowski where this is explained in detail how this works.
You introduce, so you're using these, so for multi-cells, for let's say n cells, you use n of these phase field functions.
Yes.
And wouldn't it be possible to use just one phase field function?
Yeah, that's a good question.
Oh.
Yeah, we also use one phase field,
Yeah.
but the problem is if they are close enough, then they will merge.
Yeah.
So you have to think about these boundary conditions. So there was one approach to use an inextensibility condition, which means that the surface divergence of the velocity field is 0, and you can show if this is if it is 0 and cells are close enough, then they won't merge.
Yeah, exactly. Yeah.
So there was an approach of this inextensibility condition in a paper of Sebastian, and we applied it to our model, but for this it doesn't work so nicely. So we also saw cells which coalesce.
If you have the Gauss curvature and the energy, then it's unfavorable to change topology. Perhaps you don't much, because topological transitions then are not. You see them if you keep the Gauss curvature in the Helfrich energy.
You mean in this problem here, or in?
Yeah, you still have the Helfrich energy describing the membrane.
Yeah, sure.
And if you keep the term with the Gaussian bending rigidity, then you see changes in topology, because so perhaps that helps here. Rather than dropping that term, if you keep it, then maybe you can use a single.
Yeah, I've seen a paper of two where they try to calculate these Gaussian curvature, but does it work properly? So is it?
There's a paper by Roger and Dondel where they try something to fix topology of a phase diffuse interface, but that uses a different approach. But you think if you just kept the Gaussian bending energy, you might see.
Okay. Okay, that's a good point.
You have changes in topology. That happens, right? When you have interchange of material between cells, you have these extensions forming. So it might help in understanding that.
Oh, okay. Yeah, but does it also occur for red blood cells, for example, or vesicles?
I don't think, but
yeah.
For bacteria,
okay.
It's a mechanism for what they call horizontal transport.
Okay.
And well, you have filaments forming between two cells, and they interchange
okay.
material. And they form like channels.
I think about it. Thank you. Yeah. So this was the approach, and yeah, we wanted to apply this to a problem in biology, which is called white blood cell margination. Yeah? And the idea of white blood cell margination, or what's going on there, is that for moderate hematocrit values, which means the amount of red blood cells in the fluid, that we observe that these red white blood cell moves towards the wall, adheres, and then moves to the wall into the tissue. Yeah, and the crucial role, how this happens, is that because of the different mechanical properties of the cells, they have different lift forces. Lift force is a force which acts perpendicular to the streamlines. Yeah, and because of these different properties, they have different lift forces, and this means that in this case, red blood cells have a higher lift force, so that means they move to the center of the vessel, and the circular shaped white blood cell has a lower lift force, and that means after dozens of collisions with the red blood cell, the white blood cell is pushed to the wall. Yeah, and there were a lot of simulations done, and we wanted to find out if our model works and reproduces these findings. Yeah, and first I'd like to mention that we consider here 12 red blood cells, 1 white blood cell, and the first approach is that this white blood cell is not a vesicle or a particle with a bending energy. We consider it as a rigid particle. Yeah, and there is a nice paper here where they describe these particle dynamics. And so what we see is, okay, we have periodic boundaries at one side, we have a constant fluid pressure, and we see that here the white blood cell.
So are they meant to interact with the white blood cell, or are they meant to interact within themselves?
They are also able to interact with the white blood cell. And then because the white blood cell is also given by a phase field function. Yeah, and then we are also able to calculate this interaction potential, which you see here, that they don't overlap with the white blood cell. And we see here, okay, the white blood cell moves to the wall, and the red blood cells, are in the vessel center, are placed in the vessel
Here
center.
I think it's necessary, isn't it, to have a different phase field function for the white blood cell.
Yeah, sure. If you have
Because
certain
properties.
physical properties, then it is necessary
It's really necessary.
to deal with different. Yeah, you could also give each red blood cell a different density, viscosity, and so on. Yeah, this.
Freedom to do that.
But there's also a level set paper where they had just one level set variable where they dealt with multiple cells. Okay. Okay, and in these papers were also findings that they saw that what happens to soft white blood cells. Okay, and then we wanted first to understand what's happening there. So we calculated these lift forces which occur, which act on these white blood cell and on this red blood cell. And what we see here is the lift force for a red blood cell, and here we see the different Reynolds numbers. And for all the Reynolds numbers, the red blood cell has a lift force which is greater than 0. And what we see here for our rigid particle, circular shaped white blood cell, the lift force is 0. And this is, you can also prove this analytically, that in a Stokes regime, Stokes equation is linear. The shape of the circular shape is circular, and then you can show that the sum of all forces acting perpendicular to the streamlines is 0. Therefore, we don't have any lift force. But for flexible particles, they break the symmetry because of their flexibility. Therefore, we observe a lift force. And this was also mentioned in literature. What happens if the white blood cell is soft? So we consider now a white blood cell, which is a vesicle, a small bending rigidity, and of course, again, with surface tension, the red blood cells are dealt with a surface conservation term. Yeah, and then we see that the white blood cell deforms a bit. Yeah, and non-margination occurs. Okay, nice. And what we also found out is that if we increase the Reynolds numbers for these rigid particles, they then also have a lift force. And there's also a name for this, which is called Secret-Silberberg effect. Yeah, where they found out that even for circular particles that they have a lift force, yeah, for higher Reynolds number. And we also wanted to find out if our model can reproduce this finding. And this is done here. So we now have a Reynolds number 10. The first Reynolds number was 10 to the minus 4, so Stokes regime. And we see here that, of course, the shape of the red blood cell is much more changed. And we don't observe adhesion to the wall here only once, but then cell again moves to the center. Okay, so hurry up. Okay, and this is, I think, just for conclusion. What happens if, or can we combine these models for multiple cells with our model for these polarization field, where the polarization field is supposed to be a solution of actin filaments, or without any physical meanings, just an orientation. Yeah, and can we, the question where, can we construct a model? And then the question is, how does the fluid flow and the elasticity of the cell influence the collective motion of the cell? And here is just a small example. So we have now multiple cells, and what you see here is the initial conditions with the polarization field, and this is randomly chosen, so each pointing in another direction. And if we start this simulation, so the blue arrows are fluid flow, and after a while we see that these cells are equal aligned and moving in one direction. The question is, how does the elasticity of the cell, or the or viscosity, or every parameter we know, influence this collective motion? So there's an order parameter, omega, which you see here, and if omega is 1, all cells are moving in one direction, and we want to determine these omega 1 for different properties of these cells. And then I'm going to summarize what you've seen. You've seen a hydrodynamic diffuse interface model for Helfrich flow in a two-phase flow context, and we applied this model to different applications for cell motility and for the description of multiple cells. And for cell motility, we coupled this problem with a diffusion equation for GTPAs, and we're able to describe membrane protrusion. And we also coupled it to a liquid crystal theory, and then we could also describe this contractile stress, which is supposed to be responsible for cell motility, and also red blood cell margination. Okay, and the conclusion, what we want to do is, you've seen the approach that the cell interior is viscous is a bit simple. So there are different approaches. For example, if the bulk is viscoelastic, what can we say about cell shapes? Sebastian is working on this topic right now. And all simulations, not this one in the beginning, but the simulation with fluid flow, where just in 2D, can we extend it to 3D? So we are working on this actually. Is it, does it make any sense to combine the models for cell motility, where we have the contractile stress and the membrane protrusion? And I'm working on the collective motion. And of course, you're always interested in experiments. Okay, and then I thank you for your attention.
I have a couple of questions. visualization, you had some like three structures.
Yeah.
Is it possible to understand the branching angle, for instance, from your simulations? Because that could be related to formation of vascular networks or other things, in which the angle plays in.
Okay. I mean, we changed these parameters and this diffusion parameter, and the result of this, we obtained a different pattern of these instabilities, of these Turing instabilities. So it means we had high concentrations along the membrane, and then we just added this term in normal direction, but I don't know if we can determine the angle, how this is working.
Just two quick questions. One is related to the stable shape that you reach when you have, in both examples, right? Could you describe that? Or I guess that would lead to a variational problem that you can try to solve analytically, the shape of the cell when you already have in some stable regime, stationary regime. Have you tried to do that or to compare with the experiments, like the shape of the cell when it's moving already?
Yeah, we didn't compare it to the shape of cells of experiments, but I know there are a lot of papers doing this, but yeah, they're not qualitative.
And just one last question: could it be extended this to three-phase? I mean, not with several other parameters, but with one northern parameter, but some vector potential, like what you have in capillarity theory, that you have three phases with like three well potentials instead of bistable.
So I know there are models for three-phase flows. So but yeah, Sebastian, do you have?
Well, there are phase field models for
Yeah.
three-phase and multi-phase flows, so I guess you could use the same ideas.
Yeah.
Are you able to reproduce like triple bonds or like?
Yeah. There are phase field models for this too.
Maybe one last question. Body forces. What type of body forces do you take into account?
What do you mean with what type? So
The F, you defined explicitly the F in terms of your variational form, but what exactly? No, can you take a specific body force, or they have to obey this law that you imposed?
yeah, they have to obey this law, and if they do it, this body force we have is minimizing this energy, this bending energy, and
the question, I mean, in reality, not. It's not clear to me what kind of forces explicitly you are taking into account that are acting on the body forces.
it's this body force is then just a theoretical force which
Exactly.
minimizes the energy.
Exactly.
Yeah. So, and we
In your reaction diffusion model, generally for getting the Turing pattern, we should take the different diffusion coefficients. But you told that for same diffusion coefficients you are getting Turing pattern. Why it is so?
Yeah, so this is the advantage of this network model where you have attachment and detachment to the bulk. And if these attachment and detachment parameters are kind of different, then you observe this pattern equal with equal.
This will not be possible without the interior, without the bulk PDE.
Yeah, you have to consider this bulk PDE.
Yeah, without the bulk PDE, you will.
It's not possible.
So the bulk PDE is part of the Turing mechanism that's driving the patterning. Otherwise, you won't get it.
Yeah.
And could you also simplify your model in saying that because you have these diffusion equations over the boundary of the cell, and could you also say, well, let's solve the problem only with the phase parameter, your phi parameter, I think. And then, for instance, imagine that you would have a cell which is moving around in a gel, which is more kind of solid than bloodstream. And then you could have something like, imagine that you know a certain chemical signal, a gradient of a gradient of a concentration or something like that. You can model haptotaxis or something like that. Is that? I think that's quite easy to do that with your model.
Just without any.
Yeah. I think that's.
So you mean that then so maybe you have to somehow change the advection of the phase field.
Yeah.
And maybe it's.
Yeah, so I think you have to add an advection term in your phase field model, and then.
This is depending on the gradient.
Term about it. Yeah.
Yeah.
I think that could be very easy extension.
That's a good idea. Okay. Thank you.
Right, we take the speaker again.
Okay. Thank you.